Hello everyone, my name is Nges Njungle and I'll be presenting our work SentinelTouch, a lightweight privacy-preserving biometric fingerprint authentication identification system done here at the STAM Center, Arizona State University. So our outline for today's presentation is an introduction, the problem statement, limitations of current biometric fingerprint authentication systems, and then we'll look at some background concepts, look at our system design, experimentations, and then future works and every security application begins with one fundamental question: who is really on the other side of the device? And for this reason, almost every electronic device that we see today, to institutional systems to banking systems, all have some form of authentication and identification. Password authentication and identification lays the foundation for most applications today, simply due to the simplicity of designing password systems and the theoretical soundness of these systems. However, one has to memorize passstrings, as well as passwords can easily be forgotten, shared, or even observed. For this reason, biometric authentication has emerged as an alternative approach, where we rely on biometric threads such as fingerprints, faces, and even iris for authentication. Biometric authentication systems have actually seen widespread deployment across consumer electronics, law enforcement, and in health, with fingerprints being the most widely formed of these biometric systems, just due to its stability over time, difficulty to forge, as well as the balance between accuracy, user convenience, and easy to use. Then it is also worth noting that almost every electronic device with a sensitive interface can easily be converted into a biometric scanner. However, biometric systems are very critical because, unlike passwords, they cannot be revoked or replaced. Thus, the adoption in cloud-based systems, web applications, and public systems still remain very limited due to the security and privacy reservations. The big question becomes, how then do we build efficient privacy-preserving biometric fingerprint authentication system? We then turn to one of the fundamental approaches for privacy, which is homomorphic encryption. Homomorphic encryption allows us to be able to carry out computation on encrypted data, therefore providing us privacy of data at rest, in transit, and in communication. However, homomorphic encryption introduces significant computation and memory overhead, thus only efficient for short-depth circuits. Using homomorphic encryption in fingerprint authentication can be divided into two generations, which is the first generation and the second generation. The first generation, here we simply extract fingerprint templates and then apply homomorphic encryption to encrypt them, and then we use encrypted distance comparisons like Hamming distance or Euclidean distance to be able to carry out biometric authentication. The designs for these works are very simple. However, they endure very high computational memory overheads and then generally require very long times to process and suffer from lower accuracies. The second generation generally brings in neural networks into authentication, and then they generally depend on what we call a hybrid approach, where the fingerprints are extracted using neural networks in the plaintext domain, and then the embeddings are encrypted, stored, and matched in the encrypted domain. The advantages is that they reduce the storage and computational requirements, as well as they improve the accuracy of biometric systems. However, they are built on one assumption, that the biometric systems themselves generally actually have enough computational power to explore these large neural networks. But with what we see today and the different types of biometric scanners that we have, there's extremely limited computational power or capabilities on these systems deployed. So biometric authentication and identification in the encrypted domain face two main challenges. One, the large dimension of fingerprint images. Second, due to that, we require very large neural network models to process them effectively and efficiently. So in this work, we hypothesize that if fingerprint images are carefully pre-processed while ensuring that discriminative information is being preserved, we can reduce the size of fingerprint images and then build very small chip-friendly neural networks for fingerprint authentication and identification. So our proposed solution is a two-fold solution. One, introduce a data pre-processing step to reduce fingerprint images and then leverage the compact size of these images to introduce an HE-friendly neural network for fingerprint authentication. And then we now develop a lightweight end-to-end one-to-end identification system using full deployment pipelines. So for us to fully understand this work, we will have to look at some few housekeeping concepts. First, homomorphic encryption. So homomorphic encryption is a cryptographic technique that allows computation to be carried out on encrypted data while without decryption. So for SentinelTouch, we are going to rely on the CKKS scheme for two reasons. One, its support for approximate arithmetic computation as well as SIMD operation. And then beside the general encryption, decryption, and key generation operations, it also provides encrypted addition, multiplication, and rotation operations. So second, we have data preprocessing. In machine learning, data preprocessing is actually being used to reduce dimensionality most often and improve effective learning. And in this work, we are going to rely on one foundational approach called principal component analysis. And here we're projecting high dimensional data onto low dimensional subspace. And how we do this is by calculating the covariance matrix of the input data, and then we select the top key eigen values, forming a transformative matrix W. And then for every single input now, we take it and we project it on this transformed low dimensional space matrix W input. So we take two very popular fingerprint data sets, which are Sokoto and PolyU, and then we use the PCA to do some analysis on them, and then we discover that even with just about 600 elements in the PolyU, we are almost retaining 96% of the information, while then for like 700 and something, we have a huge chunk of our discriminative information that we retain. So we project this information on PCA, then resize the images to retain, like you can see, and then we have very low dimensional images transforming like 350 to 350 by 225 dimensional images to 28 by 28 while still retaining it. We then build a lightweight LearnNet5 neural network model, which is very friendly for classification, and then at the end of it, we extract embeddings, which can be encrypted, or we then encrypt and then send over to the server for fingerprint matching. So for our system design, we propose two pipelines. We have a hybrid pipeline similar to what we have already in the neural networks approaches, where the PCA computation, the small neural network are all carried out on the client side, and then encrypted. The encrypted is sent to the server, who carry out storage, processing using cosine similarity, and then send back results for decryption at the user side. And then we have the full privacy pipeline, where the only thing that's carried out at the user end is the PCA projections, and then encryption. Then neural networks are all processed at the server side, and they also carry out cosine similarity computations, and then results are sent back for interpretation to the client. To carry out the fingerprint matching, we depend on the cosine similarity function, which has actually been widely adopted in fingerprint authentication. And then what is the cosine similarity function? It is computed by simply taking the dot product of two vectors divided by the magnitude product of those two vectors. However, magnitude computation is actually a square root computation, which is a nonlinear operation that is very inefficient in homomorphic encryption schemes. So for us to do this, we propose a new algorithm for cosine similarity, where we reformulate the cosine similarity computation to be very efficient in the encrypted domain, as you can see. Here now we end up with just one nonlinear operation, which is the inverse square root. And then for us to carry out the inverse square root in the encrypted domain, we also propose a novel algorithm using the Newton-Raphson approximation for encrypted computation. Then we propose different algorithms for user authentication and identification. And then so for our experimentation, we are using a standard CPU setup, and then we build our system using OpenFHE, and the model is developed using Fion. Then for our accuracies and memory, we are attaining very high accuracies even with just 16-dimensional embeddings. And then memory consumption is very low across the board, because memory is one of the big significant bottlenecks of homomorphic encryption. Then in terms of runtime, we do identification in like 280 something milliseconds for our hybrid pipeline, and then takes almost 16 seconds for the full everything in the full privacy pipeline. Then we've broken down the results for all the different operations in the encrypted domain. When we compare the work to related works, we discover that we are having about 10x improvement over first generation approaches and about 2.5x over hybrid approaches. And then for our hardware deployment, we used a Raspberry Pi to deploy a Resonate 18 model, which runs in about 13.9 seconds, while our Learned model and our PCA processing takes just about 0.0135 seconds. So to conclude, this work introduced SentinelTouch, a novel approach for privacy-preserving biometric authentication using homomorphic encryption. And for future works, our plans is to explore other modalities of biometric authentication. Thank you very much.